In this video, we are going to learn how to implement Prim's algorithm. Here, I am going to use priority queue data structure in this implementation. So let me first explain why. In this slide, you can see the part of the graph that we have used in previous video. And if you remember, we have chosen a vertex as our source vertex for that run. In the first iteration, we need to take the minimum edge leaving a vertex. Therefore, we had a cut like this way. Now, we can do this operation efficiently by pushing all the vertices leaving a vertex to minimum priority queue, which use weight as ordering parameter. And when we call pop on this priority queue, edge with minimum weight will be come out. Now keep in mind, we have pushed edges leaving source vertex before the first iteration as well. For the second iteration, if you remember, we have chosen cut like this. So we have to take minimum edge out of remaining edges which leave either A or B vertices. Now currently our priority queue has edge A edge. But to find light edge for this iteration, we need to push edges leaving B vertex as well. So if we push edges which leave B vertex at the end of first iteration, then the pop function call in second iteration will give the correct minimum edge. Okay, let me generalize what we are doing here. In each iteration, selected edge will have a vertex which haven't incident with any of the edges in MST prior to this iteration. So we have to push edges which leaving that particular vertex to our priority queue. Now that's what we did for edges which leave B vertex at the end of first iteration. Okay, let's look at the pseudocode for Prim's algorithm now. In this pseudocode, first three lines are almost similar to the lines in the Kruskal's algorithm where we initiate our MST set and vertex set map. In line 4, we are constructing our minimum priority queue. And then we have to add all the edges leaving the source vertex to that priority queue. And then we are going to iterate in a while loop until that priority queue is empty. Inside this while loop, we are going to pop an edge from priority queue, which will be the remaining minimum weighted edge. And then we are going to check the sets for n vertices of that edge. If both n vertices are belong to same set, then we are going to ignore this edge. Otherwise, we are going to add this edge to our MST set and union the sets those n vertices belong to. And finally, we are adding all the edges to priority queue, which leaves the n vertex whose did not incident with any edges in MST set prior to this iteration. Okay, let's now look at the implementation. This implementation is almost similar to Kruskal's implementation. Since the Prim's algorithm takes source vertex ID as input argument, we have to first find out the corresponding vertex using initialize and find vertex function as we did time and time again. Then I have created my vertex map array, which is going to store the vertex and sets that vertex are belong to, and I have initialized that array so that every vertex belong to a set which is denoted by its own ID. Then I have my priority queue, and after constructing this priority queue, I have added all the edges leaving the source vertex to this priority queue before the while loop. And then inside this while loop, first I have pop an edge from our priority queue and find out the sets that the n vertices for that edge belong to using find set function, and then I have compare those sets. If those sets are different, then I have added the edge to MST set and then union the sets that those n vertices belong to. And finally, I have added all the edges to priority queue, which leaves the n vertex whose did not incident with edges in MST set prior to this iteration. Okay, this is how we are going to implement our Prim's algorithm. Now, if you run the main function associated with this video, you will see the output minimum spanning tree is same as what we did achieve with the Kruskal's algorithm. So that's it for this video. Thank you.